Okay, thanks a lot for the introduction. It's a pleasure to be here today. Okay, so I recognize that there are various people are coming from various backgrounds in this room. So my first slide goes straight to the experts. This is the main result. Okay, and now for the people who would like a more gentle introduction. First, we're going to talk about zero knowledge. Zero knowledge is the counterintuitive principle according to which it's possible to prove something without revealing any information other than the truth of the statement itself. And I have a fun little example. Waldo is a character that's well known in children's literature. It's a find and seek type of book, and actually originally he's from the UK. His name is Wally, and he has various names in different countries. Okay, so here's my book. And this example comes from Applied Kid Cryptography by Moni Nauer and Reingold. Okay, so we consider a real-life cryptographic problem, how to convince people that you know where Waldo is without revealing information about his location. Okay, so for this experiment, I'll be Alice, and each of one of you will be Bob. And I'd like to prove to you that I know the location of Waldo on this page. Here's the page. And without revealing any information about his location. So like, you shouldn't learn his specific location in the book. For instance, you shouldn't be able to point to him yourself, etc. So I have a large piece of fabric. There's a hole in the middle, the size of Waldo. It should be twice the size of the book. Okay, this is going to be difficult. Yes, please. Okay, so don't look. Okay, so you can all see it? Okay, so this little example, you can kind of be convinced yourself that there's some sort of security going on here because you've only seen him and nothing else. I can even introduce a little bit of how we formalize security in terms of zero knowledge. So we usually talk about a simulator, and imagine that you would be the verifier, possibly cheating verifier. Imagine that you'd be able to reproduce the event that we just saw without needing the help of the prover herself. So without actually needing to resort to some sort of computationally difficult thing here, which is to find Waldo. So what you could do, if you were this verifier, you'd be called a simulator, and you would draw yourself a little picture of Waldo on a piece of paper. Everybody knows what he looks like, right? And you would do yourself this thing, right? And this looks pretty darn similar to the original thing, right? Especially if it's covered. So that would be your simulation. That would prove security. Okay, so that's the physical zero knowledge. To be a little bit more concrete, let's talk about a problem that actually has a zero knowledge proof. And this one is really well known. It's called graph 3 coloring. Okay, so the prover is given a 3 coloring of a graph. So this is colors assigned to the vertices such that every edge has 2 different colors on each side. And for a zero-knowledge proof system, what the prover first does is that she changes the labels, changes the colors to a new, there could just be a permutation, but I decided here to give different colors. So it just changes the colors here. And then we're going to use a cryptographic primitive called commitment. You may have heard of it in terms of bit commitment or string commitment. And think about this in terms of a safe or a strong box. So you put a color or a string into this safe and give the safe away to the verifier, which allows you at a later time to use a key, to reveal a key that would actually open the safe. And the point being that once the information is in the safe, it's committed to, you cannot change it anymore. And then in the verification stage, the verifier chooses a random edge of this graph and asks the prover to open the safe at those two locations. For instance, here. And the condition, of course, should be that the two vertices that are open should have different colors, because this is about a 3 coloring. Okay, so interesting things. Well, actually, first of all, things that you would need to satisfy in order to call this a zero-knowledge proof system. First of all, completeness. Every proof system should have this, even if it's not zero-knowledge. So if the graph is 3-colorable, there should exist a prover that will make the verifier accept. In this case, it's pretty simple. The prover should just use an honest coloring that's known and use that in the protocol. Okay, soundness. If the graph is not 3-colorable, then the verifier should reject with a certain probability, a bounded probability. In this case, we can bound this by 1 minus 1 over m, where m is the number of edges. And the reason why we can do this is that the graph is not 3-colorable, so there's no way to have the verifier accept every possible edge, because otherwise the prover would indeed know a 3-coloring. This does not exist. So that's where you get the 1 over m, or 1 minus 1 over m. Okay, the tricky one is, of course, the zero-knowledge property. So in this interactive proof, how do we know that the verifier does not learn anything other than the statement itself, whether or not the graph is 3-colorable? And this is where the simulator idea comes about. What we do is we show that for every possible verifier, including cheating verifiers, that's why it's called V prime, there exists a polynomial time simulator such that the channel is induced either by the interaction with the cheating verifier or with the simulator. They're computationally indistinguishable. We're talking about computational zero-knowledge. And in a nutshell, for this interactive proof system, the simulator is relatively simple. What the simulator does is to commit to a fake coloring. This is an example of fake coloring. So all the vertices are white, but there's one edge that actually is colored, and that satisfies the condition that the verifier would check if the verifier were to ask for this edge. Okay, and then the simulator runs the interaction, so runs the protocol between the verifier and the prover until the verifier asks to open an edge. And basically what the simulator has done is that the simulator has bet that this is the edge that's going to be open. If that edge is not E, then the simulator rewinds, so returns to a previous point in the protocol. By the way, when the simulator is writing the protocol, he just keeps a transcript of everything that's going around, so he can just go back to the past if he wants to. So he goes, this is called rewinding. So he rewinds until this is the edge that's actually asked, at which point he will have successfully generated the full transcript of a protocol that would be accepting and would be able to emulate the transcript. So that would be establish the zero-knowledge property. Okay, so other things we can say about this protocol that we just saw is that given a witness is the 3-coloring of the graph. The prover here is efficient, and this is something that we want to have in our own work that's coming up. This is a one-round structure, sometimes called commit and open protocol. So there's just commit to the colors, and then with a challenge, they open the challenge, and that's it. An important consequence of the fact that 3-coloring is NP complete, and now we have a zero-knowledge proof for 3-coloring. Now that this implies that all languages in NP have a zero-knowledge proof, assuming these commitments. And this was a very fundamental result to all of cryptography and also complexity theory, because based on zero-knowledge proofs, we can have more elaborate cryptographic primitives, such as two-party computation, multi-party computation, etc. There remained an open question until about 10 years ago, was that are these proofs secure against quantum verifiers? And the main obstacle was to find an alternative to rewinding. So rewinding does not work in general, rewinding does not work in the quantum scenario. So Watrous solved this problem and showed that this interactive proof, it's a classical interactive proof, and it remains secure if the verifier is quantum. Okay, so now I can flash our main theorem back up on the screen here. We talked about, this is kind of interesting, right? Because the three coloring establishes all of this result, except we talked about NP, which were efficiently verifiable witnesses by a classical verifier and classical witnesses. We talked about how they would lead to zero-knowledge proofs. The result in this work that I'm presenting today is zero-knowledge proofs for QMA. QMA is the quantum analog of NP, so it consists of a quantum witness and a quantum polynomial time verifier who's going to verify that witness. So one of the, possibly the canonical QMA complete problem is called K-local Hamiltonian. The details are not that important for what we're going to do coming up, but basically we have a Hamiltonian, and we want to determine some property of the minimum eigenvalue, and each term of the Hamiltonian acts on at most k qubits. And one of the founding results in this area is that if k is equal to 5, we have a QMA complete problem. There's lots of other QMA complete problems, not as many as NP complete problems, but we're working on it. But when we started this research project, we surveyed all of them that we could find. Actually, there was a nice survey on the archive that we found to help us. And none of them seem to have this nice structure that three coloring has. Basically, three coloring has this uniformity of the coloring marginals, and that helped us build this really simple zero-knowledge proof. So we had to find some alternative solution. There is one exception, density matrix consistency by Liu seems to admit a natural zero-knowledge proof, but this problem is QMA hard under Cook reductions only, and usually we need CARP reductions to talk about QMA completeness. So what are we going to do? Here are the main tools we're going to use to build zero-knowledge proofs for QMA. First of all, we found a new QMA complete problem called local Clifford Hamiltonian. It's similar to local Hamiltonian, but only Clifford operations are required when we're doing the verification of the Hamiltonian terms. So I'm not going to go into details of this tool that we use, but it is a new result. It could be useful somewhere else. Another tool that we use is a quantum message authentication code. So we're going to use Clifford verifications, and what was really useful, and the reason why we looked into quantum message authentication codes, we wanted a method to be able to apply Clifford gates to encoded data, such that, as well as measurements, such that any deviation would be detected. And there are techniques known that would enable a certain gate set, but not all Cliffords. So we have a new message authentication code to allow that. And we are also going to use existing quantum secure classical tools, namely zero-knowledge proofs for NP, as I mentioned previously, that were established by Watrous, and coin flipping by Damgard-Luneman. And one of the main ideas in our interactive proof is we split the proof into a quantum part and a classical part. And we use these classical tools on the classical part. Okay, so here's what the interactive proof looks like in a nutshell. The prover is given a n-qubit input, and it's a witness, a quantum witness to the local Clifford Hamiltonian problem. She encodes it into this authentication code by using a key K, and she sends the quantum registers to the verifier. She also commits using a classical commitment to the keys K and sends the commitment to the verifier. Then they interact in a coin flipping protocol in order to randomly generate a string R. They both get the value R. And R determines which Hamiltonian term is going to be verified by the verifier. In order to verify, well, I should not use verify. This is overloaded in this talk. So in order to do this Hamiltonian term check, the verifier does this transversal Clifford that is tolerated on the authentication here. On the rth term, it does a measurement and sends the classical measurement result back to the prover. And then the prover uses the knowledge of the key for the authentication code to verify that the measurement was done honestly. Of course, the Clifford and the measurement. And then we go into a classical zero-knowledge proof between the prover and the verifier that, for the statement, if M were to be decoded with the key K, then we would get an accepting state. And in this picture, I would kind of assume that each of these boxes accepts. So if we arrive at the end, then it'll be accept. And if there's a reject here or reject here, then the verifier rejects. So the properties of the proof system, just like three coloring, completeness is pretty straightforward. If this is a valid witness, the verifier is going to accept. Soundness is a little bit trickier. The main idea is that we're able to show that whatever the prover sends, it can be decoded into a witness that has an acceptance probability no smaller than what happens in the zero-knowledge proof system. Okay, now the properties that's desirable is that this is a one-round commit and open protocol. And an overview of how we're going to build a simulator to establish the zero-knowledge property is the following. So here's our original protocol. We will replace one after one the pieces in the protocol by their ideal versions for which we know security holds. So for instance, the coin flipping replaced by an ideal coin flipping. The zero-knowledge proof, that was a classical zero-knowledge proof replaced by its simulator that exists by the properties of the zero-knowledge proof. At this point, we don't really need the commitments at all because we've gotten rid of what we do with them. So let's just commit to some fake input. And since we're at it, let's also create a fake witness, kind of like that fake coloring. This is going to be a fake witness that is guaranteed to pass the rth term test, but nothing else. Oh, but R is nicely coordinated with this R. So all we need to do now is to use the property of the quantum authentication to essentially guarantee that the verifier is going to be honest. So basically, the quantum authentication ensures that if the verifier is cheating, we're going to get a reject here at this point. So basically what happens is that the only thing the verifier will see will be this rth term that was created fake, but the verifier, of course, can't tell, and this will lead the verifier to accept. Okay, so that was the main idea of the interactive proof and the simulation. So here's the main statement. Hopefully you're in a better position now to be able to understand what it means. And future work that we'd like to work on, or that maybe some people in the room will be able to solve. First of all, I talked about the desire to look for a natural QMA complete problem that would be zero knowledge, something closer to three coloring that would maybe not require the authentication, but that would have this nice symmetry to have a more natural proof. Another question would be to have zero-knowledge proofs of quantum knowledge. So what happens in this case is that we typically ask for an extractor that would be able, given the interactive proof system, the extractor would be able to actually extract the witness. So this is a stronger property than zero knowledge. It's basically a proof that you not only of the truthness of the statement, but that you actually know a witness to that statement. Thanks a lot.
Let's have one quick question.
Can you say a bit about? Can you say a bit more about this local Clifford Hamiltonian? Do you mean the time evolution is Clifford, or terms are Clifford?
The local Clifford? Not really. Don't know exactly how to translate it to the time evolution, but it's that when you do the projector, then it's a Clifford operation. So like this.
Terms in the Hamiltonian, there are Clifford operators?
Yes, exactly. So they're like projectors onto zero and then a Clifford onto them. Yeah.
Do we have one more? Otherwise, let's thank Anne and all the speakers of this session.